Hey guys, and welcome back to the LibGDX Java tutorial series. In the last part, we dig deep into the tiled program and made our first tiled map. I updated it a little bit. I still did not copy over the original map from the repository. I will do that to the next part. And for now, it's just like that, a little adjustment. And in this part, we are going to do some basic groundwork. So finally, we are really going to implement some code in our core project and try to render the tiled map that we have here available. We try to render that in our window, that we have something available and not just a black window as we had it initially. And yeah, so in this part, I introduce some generic topics which are useful for any game. And yeah, so let's start with that. So first of all, we need to go to our main class, which in my case, I call it GDX Game. It's in the core project, and it's this one here, which extends the game class. So what is that first of all? So in LibGDX, the entry point or the main class of any application is a so-called ApplicationListener. And an ApplicationListener simply has a couple of lifecycle methods that you can see here. So create means, let me also, okay, it automatically downloads the sources. Okay, so it has a create method, which is the entry point where you can start creating your own objects and everything, because before create is called, we don't have an OpenGL context, which is the graphic context for the LibGDX game to render any sprites or any graphics, and also the audio context. So OpenAL is used there. Also, that one is not available. So if you want to interact with resources, render something, play some audio, then you can do that only after the create lifecycle method is called. Then there's a resize method. That one is simply when you, for example, change your window to full screen, or if you resize it, then resize is called with the new width and height of the window. We learn what we can do here in that part and why that one is important. Then the render method, which is simply like the game loop. So every frame, every update, this render method is called. And there you put basically all the logic of your game that needs to update every frame. So the render method is the method that gets called every frame. Pause and resume, I think they are not important for the desktop launcher. They are more important for the Android launcher. So if you have your game on a mobile phone and, for example, your mother is calling you and the game goes into the background, then the pause method is called. And when you go back to the game, then the resume method is called. And finally, the dispose method, that one is important to free resources that we are going to allocate. So resources in that context is not like a Java object or something. That one is still normally freed up by the garbage collector by Java, but the resource would be something, for example, a texture. So if we want to render a graphic to the screen, then we need to load a so-called texture, and that would be a resource which is bound to the RAM. And we need to free that to free the RAM space of the texture, or also a music file or sound file. There are a couple of resources that you need to load, which occupy some RAM as mentioned. And in the dispose method, or with the dispose call, you can free up those resources to avoid memory leak. So that is the application listener, which is an interface. Then, since there are a lot of methods and sometimes you don't need all of them, there's also an application adapter, which is a typical pattern in LibGDX. So for every interface, they usually have an adapter class where they have simply a default implementation of all the methods, so that you only need to override the things that you really want to override. I think the reason why they have this adapter pattern is that LibGDX was created before Java 8 and there were no default implementations for interfaces. So that's why they had this adapter approach to have this flexibility with the override of the different methods. But when we come back to our game, you can see that we are actually extending a game, which is not an application listener and not an application adapter. You can see it implements the application listener. So basically it is an application listener, but a special kind of implementation. And that one is usually what I use, and I think what is recommended for games. So what is a screen? You can simply imagine it as a specific part of your game. So for example, the main menu would be a screen. Maybe the initial loading of some resources would be a separate screen. Then where the game itself is running, that would be a screen. Then maybe if you have a separate combat window or combat transition into a separate screen, a game over screen, whatever. So specific parts of your game can be made as a screen, and the game itself is simply an implementation where you can, it's a very simple implementation where you can simply set an active screen, and then the pause, resume, dispose, render, resize methods of the application listener interface that we have seen before, they are then simply forwarded through to the active screen. So if there would be a screen set, then the hide, pause, resume method and so on of the screen is called. And besides that, there is a set screen to set the active screen of the game, and a get screen to also get the active screen. And while this is, I would say, good enough as a starting point, in my opinion, it is not that good enough for a real game. And what we are going to do now first is that we are going to implement a so-called screen cache. This is if you come from my Kotlin tutorial series maybe, and you are watching this one here as well. It's basically the LibGDX game extension or class where you can, instead of just having one active screen in your game class, you can have infinite amount of screens. So you can register screens like a loading screen, a game screen, combat screen, whatever. And you can still set an active screen as well. And at the end, so when the dispose method of the game is called, then simply all the screens which were registered before, all their dispose methods get called as well. So it's I would say a little bit of a convenient function, and very important, or at least for me, it's always important and nice to have it available in my game. So we will start with that. So currently we just have our set screen method with the first screen, and now we are going to implement this screen caching mechanism. So what we need here, basically, it's just a map, so we can have a final map. And the key of this map is a class of anything that it extends the screen interface. And the value is then a specific screen, and we can call that screen cache, and we can also initialize that here with a hash map. So that is the backing data structure of our different screens. Maybe some people which are familiar with LibGDX, also to just mention that here, LibGDX has a lot of their own collections. So for example, object map is one that comes to my mind. There are a couple of other collections in LibGDX, like a special array implementation. And yeah, in my opinion, so at least from my understanding, they were implemented also back then for optimized performance and also to reduce the garbage collection, which came back then with the normal Java collections. But in my opinion, that has changed quite a lot since the old days of Java, and also the modern garbage collector is way more powerful, especially when it comes to short-living objects. So in my opinion, it's not always necessary and needed to use the LibGDX collections. And in my opinion, one mistake that they made, or maybe that was not available back then, all their collections, they don't implement the common Java interfaces. So an object map doesn't implement the map interface, for example, in Java. So all the methods that are available, like stream or mapping or whatever, which are available there, you don't have that with the LibGDX collections, which is a little bit of a downer for me from time to time. So that's why I normally just use the normal collections which are available in the language, in Kotlin, the standard library, and also in Java project here. And only if I face any issues, so if there would be performance issues or maybe a lot of garbage collecting or anything, then I start to optimize the game. And this is also the second hint or the thing that I want to give you on your journey with game development. Don't try to optimize your game at the beginning. Of course, don't implement a garbage solution. Think a little bit of what you're trying to do and try to implement it in a good way. but don't over-engineer and over-optimize everything as long as you don't know if it's really a bottleneck. So you don't need to have a perfect code for a game to work. That is not necessary. And yeah, so that's the reason why I here use just a normal hash map and not the libgdx object map, for example. Okay, then, as mentioned, we need two methods. We need one method where we can add a screen, where we just pass in a real screen instance, and we then just put that into our screen cache like that. We could add here some safety that we don't add the same screen twice and so on. Would be possible to be on the safe side, but yeah, we skipped that here because most likely you see that in a moment, the code where we are adding screens and where we set screens, that is just one specific area, and it's, I would say, almost impossible to mess up, so we can avoid here the safeties. But of course, if you want to have again some sanity checks here and to be on the safe side, then please feel free to add here some special corner cases where you check if it is already part of the cache, for example. Okay, and the second method would be the setScreen method, where now we just want to add the class, so the class instance of the screen, and not the screen instance itself. And then we simply get the screen from the cache. So that is our screen. And if the screen is null, then it was not added before, so not registered. That would be a problem. And in libgdx, there is a special runtime exception that we can use here. It's the GDX runtime exception. And then, for example, here, no screen with class, screen class found in the screen cache, for example. Something like that. So there we have an exception if that is really happening, and we want to avoid that. Other than that, so if there is a screen, then we just call the normal setScreen method of our game class. So when we go into here, you see that it then simply calls the hide method of any screen which is currently available. Then it sets the new screen as an active screen, and it calls the show and resize method with the current width and height of the window. So that is the normal behavior of the game class. So that's why we call here super setScreen. Okay, and finally up here, so instead of just have here setScreen first screen, our API will then look like this. So we add a screen, which in our case would be the first screen. And then once we have registered the different screens, we can set an active screen like that. So with setScreen first screen class. That is the change. And currently, of course, we have now here an additional method that we need to call compared to what we had before. But in a couple of parts, when we add then also a loading screen, and maybe in a real game where you have then more screens available, then this approach here, I personally find that way better than the base implementation that we have with the game class. Okay, then let's rename our first screen because that will be our real game screen. And normally what I also do, so when we go or when we create a specific screen, then we pass in the GDX game, the application itself. Why do we need that? Because the game class, also in a moment, will have instances of a couple of other classes or objects that we need, like for example for asset management and also for rendering and so on. And when we pass in the game class, then we can get all these objects out of it. And also what is even more important, if we want to change from the game screen to another screen, then we need to have access to the setScreen class here. And that's why almost every screen will need a reference to our game class so that we can switch away to another screen. That is the most important thing. So for now, I just leave it here broken, but we fix that then in a moment. Good, then as mentioned, we also need a couple of other things. So first of all, let's start with a batch. What is a batch? So in our case, a batch, we will create that here, is a new Spritebatch. this is, as the name suggests, the class which is then responsible to render graphics to the screen. Maybe you never heard the term sprite. A sprite, to put it very simple, you can imagine it like a graphic, for example, a Super Mario graphic, and the sprite simply also has the information of the position where it should be rendered, the color with which it should be rendered, the rotation, if there would be any rotation, and things like that. So that's why it's called a sprite patch. And why is it a patch? We will also learn that then when we go deeper into the rendering stuff of LibGDX, we can basically then batch together the different render calls that we need to do to a graphic. So normally in OpenGL, when you render a graphic, it binds this graphic, the texture, to your graphics card. Then it can do some rendering to the screen. And when you have the next image, it needs to swap this texture binding to the next texture and makes a render call again. And with this batching mechanism, we learned that then in the future, we can optimize that. And instead of always swapping these textures and making a call one by one, we can batch them together, send a lot of data to the graphics card at once, and render the entire screen or scene very efficiently. So that's the sprite patch. That is the important thing for rendering. And as we learned before, so there's a dispose method, which we are going to override now. And in this dispose method, we need to dispose our batch, of course. And what we have also forgotten, we also need to dispose the different screens that we have in our screen cache. So the different values, so the different screen instances, and for those we call the dispose method. And we can also, at this point here, we could clear also the cache because it's no longer important. And yeah, after that we dispose the patch, and finally we call super.dispose, which I think is not really necessary. So it would call from the screen the hide method if there would be still an active screen. But I think we don't need that. So let's just remove it for now. I think it's not necessary. Okay, next thing. So after next to the batch, we also need something again when it comes to rendering or when it comes to our game, which is a so-called camera. So there we will have an orthographic camera, because we are working with 2D top-down view. And we also need a viewport for our game. And yeah, what is that? So you can imagine it like this. So when you have a game in front of you, so when you have a window and there are some graphics, again, imagine, for example, the Super Mario Brothers scene, then from a player perspective, you see just a specific part of an entire level. And this is very similar to like you would when you make a video with your phone. You simply have a camera. The camera has a specific size and a specific position. And the thing that the camera is currently seeing, that is the part of the game that is currently rendered to the screen. So that is the camera. And the viewport simply then contains a camera and has some mathematical stuff in it in order to render the things then to the screen with specific or different strategies. So one strategy could be that we just want to stretch our scene. So everything simply gets stretched so that so that the entire window is filled. That, of course, would, for example, break the aspect ratios of our graphics, and they would either look shrinked or enlarged and quite bad. Another strategy would be a so-called fit viewport, which simply tries to fit the scene into a specific aspect ratio that you pass to the viewport, and then you will have simply black bars on the left or right side, or top or bottom part. Another one would be, how's it called? I think fill viewport. That one simply extends the scene on the x-axis or y-axis, depending on where you have more space available, and simply renders then more of your game than you want, that you initially maybe have planned. That would be most likely a bad viewport for strategy games, because that would give the player with a higher resolution an advantage over player with a smaller resolution. So I will add a link in the video description below for the LibGDX viewport. So there's a video available from this guy Releos, which makes also some nice LibGDX videos. So check him out. He's a user interface expert. And on this page, you can find the different description and the different viewports which are available and what their strategy is. And again, to summarize it, so the viewport has the mathematical calculations in it to know how to render things to the screen. And it also contains a camera. And the camera simply is a position and has a specific size and describes how much of the game scene you can see. So we need to initialize that. So for us, the camera, as mentioned, is simply a new orthographic camera. And the viewport in our case is a fit viewport with a specific width and a specific height. And I usually prefer to have that here as a constant available. And we also pass in the camera. So the values that I have chosen for the width and the height is 16 and the height is 9. And here is also one thing. I usually never work with pixels because especially later on when we come to Box2D, the physics engine, working with pixels does not have, or actually has a couple of disadvantages. I will explain that in more detail in that part. But for now, for you, it's important that we just work with arbitrary game world units. So our world is 16 units wide and 9 units high, whatever that means. Usually what I take here is that one world unit is simply one tile. But of course, that can be changed. But for me, that always usually makes a lot of sense that one world unit is one tile, because that way, for example, when I define the speed of objects, I can simply define, for example, that it can move 4 units, which would be 4 tiles per second. And it doesn't matter what kind of graphics I have here or what kind of dimensions I have here for the tiled map. Could be 64 by 64, 16 by 16. One world unit is simply one tile. So we are independent of the pixels, and that is a good thing, especially later on when it comes to the physics engine that we are going to introduce then. Okay, another thing that we need to do, so when a resize is happening, then we also need to update our viewport. Because as mentioned, depending on what kind of size our window has, which is the width and the height that we get passed in here, the viewport then calculates or does something when it comes to the rendering, that it places everything correctly. And that it can do that correctly, it also needs to get updated whenever the window size changes. So that's why in the resize method, we need to update our viewport. And the last argument, this true here, that simply centers the camera again, which later on is not really necessary because the camera will stick to the player. But it's never, in my opinion, a bad idea to center that. Okay, and the last thing that I want to add is now some asset management, because we need a lot of asset management in our game. And for now, as mentioned initially at the beginning, we want to load our tiled map and render it to the screen. So we need to load this tiled map, which is also a resource, and dispose it then at the end. And you could imagine that this is quite tedious if you need to do that for all the different assets that you have available in your game. So that's why in LibGDX there's also something available, which is called an asset manager. But we don't use that class directly. We will wrap it inside our own class. And why do I do that? The reason is that in a couple of games in the past, I changed the asset manager throughout the project, because sometimes I tried out an asynchronous version of an asset manager. Then there was a special implementation for the LibGDX asset management, and I tried out that one. And whenever you change something, for example, let's imagine we use the normal asset manager everywhere in our code, and now we want to replace it with a different asset manager implementation, then we would need to change all the different areas and the code segments where we use the asset manager. And to avoid that, we will simply have our own implementation, and I call it AssetService. And that way, we just would need to update the internal things of this AssetService class when we would change the asset management stuff, and we don't need to touch all the other code segments because they will still just access the asset service, and everything that's happening internally is handled by that specific class. And yeah, for that reason, we create here a new package that we can call asset. And first of all, let's start with an interface which we call asset. And let me close that one again. Okay, and the asset itself, that is a descriptor of an asset that we want to load. Could be a music asset. In our case, would be a tiled map asset. We have a couple of those then when we come to the end of this tutorial series. And the interface simply has then an asset descriptor, which is also a generic class, and we can call that here getDescriptor. And that one here again is a basic LibGDX class, which describes an asset. So it has the information what type it is, if it's a music, a sound, a tiled map. It has the path to the asset, and optionally it can also contain some parameters. So if we need to do some special things when we load the asset, then we can use this asset parameters. We see that in a moment and use that as well. So that's why I use here the asset descriptor class for our own game assets. The next thing is that we are going to create now an asset implementation for our map assets. Okay, so here we are going to implement our asset class from before, and the type of asset that we are going to load is a so-called tiled map. And there for now we just have one map, which is the main map, and there we need a specific path to that one, which is, I called it main.tmx. So that is the name of the map. And what we need an asset descriptor. And we need to override the getDescriptor method, which returns then this descriptor. And now we just need to initialize it in the constructor. And the constructor takes, that one is wrong, that one takes the name of the map. And now we can create a new asset descriptor instance. And we have all our maps in the maps folder of the assets, maps, and below here we have then the different maps. So it always starts with map/. And then the map name that we pass in here. And again, it's a tiled map class asset. Oh, and of course, it's not a class, it's an enumeration. And then we need to remove the public keyword here. And that's it, of course. So we have now an enumeration for our map assets. And I use that approach then for all the other assets as well. We will have a music asset enumeration for the different music assets, sound asset enumeration for the sound assets, and so on, so that we don't need to remember the hard-coded paths all the time, and can just work then with the enumeration constants. Okay, additionally, because if you remember from the last part, we used a so-called tiled project, and there is a feature that we are also using, which are the classes and the enumeration properties in tiled. And this information here is stored in the project file of tiled. So when we come back in this, I called it tiled project. In this project file, you can open it. It's also just JSON, if I remember correctly. There is some information, for example, here for our object type, which is an enumeration, and what kind of values it has, also for the class and so on. And in order for LibGDX, of course, to load that then correctly when we load the tiled map, we need to tell it what kind of project file it needs to take as a reference, because the project file is not referenced in the map files itself. So in the main TMX file, we don't know that it's part of the project. So that's why we need to tell LibGDX where to find it. And for that, we can use from the TMX map loader, which I also explain in a moment, that we can create parameters. And from that parameters, we set the project file path, which in our case again is maps, and then tiled.tiled project in my case, whatever name you have there. And that would be the third argument of the asset descriptor, just like that. Okay, and finally, we want to implement our asset service. Which is disposable. So this disposable is also just an interface in LibGDX, which indicates that a class is a specific resource that needs to be disposed. In our case, that would be the asset service. And for now, the implementation that we are going to use is the asset manager from LibGDX. But again, the advantage of this approach is that in the future, if you maybe want to roll your own implementation or change to a different one, then you can do that and just need to adjust the code with the asset service itself. Okay, so we need a constructor there because we want to align with how the asset manager is created in LibGDX to have a similar experience, API experience. We pass in a so-called file handler resolver. And then we create a new asset manager instance and pass the file handler resolver. The file handler resolver, there are a couple of implementations in LibGDX. There is, I think, a local file, I forgot the names, but I think there is a local file handle resolver which looks up assets relative to the root of the project. Then there is an absolute file handle resolver where you need to pass in the entire path. Then there is, I think, a specific class loader, file handle resolver, and things like that. Yeah, we will see what we pass here then when we create the instance in the game class. And an asset manager itself has built in some defaults for specific objects that it can load that. So for example, it can already load textures, music, sound files, and so on. But for tiled map files, we need to tell it what kind of loader it should use there, because a tiled map can be created by different programs out there, and there are different loader implementations in LibGDX. And in our case, since we are using the TMX file format, so the XML file format of tiled map, we tell it here that for any tiled map that we want to load, we want to use the TMX map loader. Here, just for you to know, there's currently an open pull request. Maybe it's already merged, I cannot remember it, that you don't need to distinguish here between a TMX, and I think the other one is called TMJ map loader if you use the JSON format. In the future, there will be just one loader. I think it will be then called tiled loader, if I remember correctly. And that one simply then knows by what kind of path you have in your map file. If it's TMX or TMJ, then it knows what kind of loader it needs to use. So you don't need to decide here what kind of loader you want to have. But we don't have that yet. So in our case, we need to tell it that we want to use the XML loader. Okay, and we need to implement the dispose method, where we simply call the dispose method of the asset manager of LibGDX. And finally, we want to define a couple of methods. So for now, we just need a load method where we pass in an asset of type T. And when we have that, then from our asset manager, we load the asset via the asset descriptor. What this does is it queues a task in the asset manager, because the asset manager would be asynchronous, and you would need to call update all the time. So for example, in a loading screen in the render method, which is called per frame, you would need to call asset manager update to update the loading of the different resources. But here we will do some convenience method to make it a little bit easier. So just if you want to load, for example, here the tiled map, which will be super fast with modern hardware in our case, we can call here after we made a call to load, we say here finish loading, so that the loading is done. And finally, we simply return then the asset from the asset descriptor and get the tiled map here directly back. So that is a little bit easier to handle then. Okay, another implementation or another method would be to queue a resource or an asset. So there we simply call load without the finish loading. That method will be used later on in the loading screen, where we load then a couple of assets before the real game starts. And we do this asynchronously with the asset manager. And another method that will be useful is also a get method to an asset, where we then return the asset from the asset manager. And again, later on in the loading screen implementation, we don't need that now, but we already prepare it here. Here we will make a call to update of the asset manager. And finally, what is also useful when we exit our game, or if we want to debug what kind of assets are already loaded and things like that, we can debug the diagnostics. And that one we will log as a debug information from our asset service. We will get the diagnostics of the asset manager. We see that then when we run the game, what that means. And here, just that you see it here, this is the way how you print a message or log a message in LibGDX. You have GDX app, then there is debug for a debug message, log for a normal log message, and error for an error message. And it always takes in a tag, which is usually the class name where you call this method. Then the second argument is the text that you want to display. And I think there's a third argument, exactly, where you can pass in an exception if you are inside a try-catch block. Okay, but that's it for our asset service implementation. So coming back to our game, we also want to have here an asset service reference. And we create that here, create a new asset service, and we pass in an internal file handle resolver, which, from what I remember, simply looks up resources inside the assets folder. I think this is the internal file handle resolver, if I remember correctly. And we should not forget to also dispose the asset service in the dispose method at the end. And maybe also additionally, whenever we exit the game, we also want to debug the diagnostics so that we see what kind of assets are or were loaded and which were still kept by the game itself before we dispose everything. Good, I think that's almost it. So what we need now, we need the different getter methods in Java. So we need a get batch, we need a get asset service, we need a get viewport, and we need a get camera. Good. And finally, let's go to our game screen now and update this implementation here. So first of all, let's throw away all the different methods because we don't need them at the moment, at least not all of them. Also the combat at the beginning, let's remove it. So the first change is that instead of the screen interface, we will have a screen adapter. Again, same approach or same pattern that we have seen before. The screen adapter is simply the screen interface with a basic implementation that we don't need to override everything. Then we need to hold a reference to our game so that we can change the screen later on if needed. We need to have a reference to our asset service. We need to have a reference to our viewport and maybe also the camera. And I think for now that's it. So let's create a constructor. We don't need anything of that because the only thing that we pass in here is our game. And then we can get simply everything from the game class. Good, then when our screen gets shown, so this is when the screen gets active, then for now we want to load the tiled map. So we have here our asset service and we want to load our main map. And that's it. And then we need to override the render method because now we want to render this tiled map. For that, we need another class which is called an OrthographicMapRenderer. So there would be a lot of different tiled map renderers available for hexagonal tiled maps and all the different types that we have seen in the last part. Since we have an orthogonal tiled map, we will use the orthogonal tiled map renderer. Let's call that map renderer. And this map renderer is then a new instance of that. So where we pass in the map, I think, isn't there also, we also need to pass in the patch. Yes, so map, unit scale, and patch. We don't have a reference to the patch, so let's also get that. Okay, if we would not pass here the patch, then the tiled map renderer internally will create another Spritebatch automatically, and you should try to avoid that. So normally you just need one single Spritebatch for your entire game. It's quite a heavy resource, so try to don't create too much of those. And again, I think normally you just need one of them. And if I remember correctly, this is then also has a dispose method, which I think it does nothing because, yeah, as mentioned, it doesn't own the patch because we pass it to it. So it doesn't call here batch dispose, but still as a best practice to not forget it. And if the implementation maybe changes at some point, we will call that here. Unit scale. This is now an important thing because, as mentioned before, our viewport doesn't work with pixels. We work with game world units. And the unit scale here simply specifies now the relation between pixels and our game world. And in our case, we just want to have that one tile, which, let me check again, I think is 16 by 16 pixels. Yes, here, 16 by 16. So the unit scale would be 1 divided by 16, so that one tile is then really one world unit wide and one world unit high. And this unit scale value here, since we also need it later on in other parts of the game, we will also define it here as a constant. So it's 1 divided by 16. And we use that here. Okay, and finally the rendering. So, first of all, this one here is wrong. The dispose method, of course, belongs to the dispose method here. And rendering is now done the following way so that you see that. So first of all, we need to apply the viewport. That is always a best practice in OpenShell. So before you do any render calls, apply the viewport. So the rendering process in the background knows the dimensions of the window and where it needs to put everything. So there's some mathematical stuff again. And viewport apply is always important that when you use a specific viewport for rendering, which in our case would now be this viewport because we want to render our game view, then apply it. Later on, we have another viewport for the user interface. And before we do any user interface rendering, we will then call this UI viewport.apply. And yeah, just keep that in mind that that is a best practice. Then from our patch, we want to set a specific color because again, it could be that in your user interface, maybe one object is rendered with a red color and so on, which would mean when we come here to that block, the Spritebatch has a red color and would then render everything with a red tinting color. And also just to keep it sane and to don't think about that too much, always before you start rendering something and you want to have it in the normal colors as you see it, for example, in the program, then just set it to color white so that it's just rendered with the normal colors. And finally, if I remember correctly, there should be a render method on the map renderer. And also the map renderer, we need to tell it what kind of view it should have. So what portion of the map it should render. Again, as I said before, we have a camera in our game. And as an example, let's say we have a camera which is 3 world units wide and 3 world units high. So when the map renderer in LibGDX wants to render the map, we need to tell it where is our camera and how much does it see of the map so that LibGDX can then render that portion of the map, and it renders that always at the bottom left, so at the coordinate 0, 0 in OpenGL, it then renders that specific segment. So that is important to keep in mind, that the map itself, it doesn't move. It's always rendered from the origin, from 0, 0. And by telling it with the setView method and passing in our camera, it knows where on the map we are and what kind of portion of that map it should render. Okay, I think that's it. Let me try that first. If I missed something, you will hear from me in a couple of seconds. Okay, we actually made a mistake. So here we are already accessing the map, which doesn't make sense because we just load it in the show method. So here the initial map will be null. And here below in the map renderer, we can set the map. And that should fix one of the issues that I just saw. And that looks good. So we can see something. So let me enlarge the screen. So since we used a fit viewport, we have some black borders on the left and right, depending on what kind of dimensions our window has. So if you have a perfect 16:9 window, as you see it here, there are no black borders left and right. But if you have a different dimension, then the scene itself remains the same. So the aspect ratio remains the same and what we see remains the same. But LibGDX will simply add some black bars at the top or bottom, or the other way around on the right and left side. But the important part is that this area here, the game itself, remains the same and doesn't get stretched or something like that. We also see that the animated tiles are automatically working. I show that in a moment why that is working or what is happening behind the scenes. And we also see that our objects here, like the player and the tree that we placed here, they are not visible here. And I show you now why that is happening. But first of all, good job. We made it happen and rendered now something meaningful to our game and have some sort of integration already with the Tiled program, which is great. Okay, so what is happening? So why is all of that working? When we go into the render method of the map renderer, then we see a couple of things what it is doing. So first of all, begin render, end render. What is that? There's always in OpenGL, when you start with something, for example, with rendering in that case, you need to call begin to the Spritebatch. And when you are done with your different render calls, you need to call end of the Spritebatch. And this is this batching mechanism that I described. So you begin the batching process, you make then the different draw calls of your game objects, of the tiled map and things like that. And when you are done, you call batch end. And then all the different draw calls that you made inside begin and end are then sent at once to the graphics card and things are rendered. This is very simply described what is happening. It's a little bit more complex and there are some exceptions where the batch gets broken and it automatically starts another batch for you. You don't really know easily when that is happening. But I go into more detail of that in a later part. For now, just keep the simple description in mind. Begin, make all the renderings, calls, and then call end. And that's it with the Spritebatch. And also in begin render, there is this animated tiled map tile, update animation base time, which is then updating the different animated tiles that we have in tiled with the delta time between 2 frames. And that's why this animation is already working as well, because it's part of this begin render call here. And then it's very simple. So a tiled map itself contains a list of layers, which in our case would be the ground, background, object, and foreground layer. And then it simply iterates through all of them in the order as we have it in the tile program, and it calls render map layer. And then if a layer is not visible, it doesn't render it. What does that mean? So when we hide here a layer, like for example the ground layer, then this render is not shown in tiled, and this layer is then also not shown in LibGDX. This is the is visible check. And then depending on if it's a group layer, we have seen that in the last part, it does something. Otherwise, if it's a tile layer, then it renders the tile layer. If it's an image layer, it does some image layer rendering. And if it's an object layer, that is this one here, it calls render object for every map object. And render object does nothing. So that's the reason why we don't see our player and tree graphic. We will fix that later on. So for me personally, it makes total sense that the render object does nothing, because that is really game dependent. So depending on what kind of game you are implementing, you have different logic for your game object rendering. So in my opinion, it makes sense that there is no generic solution in the tiled map renderer. I know that some people were confused. I see from time to time some threads created in the Discord channel as well, that people are wondering why their objects are not shown. And yeah, this is the reason. Render object does nothing. You really need to take care of yourself, what you do with map objects in the tiled map. Okay, perfect. There are two more things that I want to cover also in this part, which is also some generic things for any game. The first thing is GLProfiler. So as I mentioned before, when we make the draw calls and so on, there's this texture binding. Maybe you want to track how many draw calls you are doing and things like that. And to monitor the performance or to track it, there is a class which is called GLProfiler, which we create now in our game. And there we create a new instance. And we need to pass in here the graphics context of LibGDX, which is GDX graphics, so that it tracks the calls that we do to the graphics, to OpenGL basically, which in our case is done through the Spritebatch. Whenever we interact with the Spritebatch, then that will be profiled. And to enable the profiling, we need to call the enable method here. Now what we need to do, we need to override our render method, which by default is just calling the render method of the screen. Where I just noticed something, it doesn't clear the screen, so that is missing. We will add that as well. So first of all, what we do is from the profiler, we reset it. So at the beginning of the frame, everything that was captured inside a frame will be reset, all these internal metrics. Then what we want to do, we want to clear the screen. So everything that was rendered before the entire scene, we will clear it with a black color. Also, we clear this color buffer bit. Like that is not correct. Like that. So this is also a buffer that is used there, and that one also gets cleared. Then we really want to render our screen. So here we clear the screen with a black color, so nothing is shown. Then we render our scene. And then finally, we can update the title, for example, of our window. Set title and call it Mystic Tutorial. And then, for example, we log the amount of draw calls, and there we use from our GLProfiler the get draw calls. There are different methods: get calls, get draw calls, get shader switches, get texture bindings. So there's a couple of information available in that profiler that you can use. For now, just as a demonstration, we will use the amount of draw calls that are used, and that's it. So now when we start the game again, we see here that the draw calls is just 1. Why is that? So that is a perfect number. You try to get the draw calls to a minimum amount. But actually, you could imagine that there are a lot of tiles called, and for each tile, it makes a draw call to the Spritebatch, and that is correct. But since our entire tile set is just one big graphic, so it's just one image, the rendering is optimized. Again, I cover that also in the later part in more detail. But what is basically happening, this entire graphic is just bound once to our GPU, and then the different regions, so the different portions here of the tile sets, the different tiles, they are then rendered in a loop in the map renderer. But since they are part of the same graphic, of the same texture, they are doesn't need to be any texture swapping. And in the end, all these calls can be batched together and they don't just get rendered once. So that's why we just have here a draw call of 1. In a later part, we will see that this number will increase at some point, and we will learn something to optimize it to get it back again to a smaller number. Usually, I think 1 is very unrealistic that you have that. In more complex games that I made, I have draw calls up to 10 or 12 then in the end with the user interface. And yeah, that one always worked quite well for me. And yeah, just to keep in mind, try to keep that number here as low as possible and don't go to, for example, 1,000 draw calls per frame. That would be quite bad. Okay, that's one way to profile something in LibGDX. Another thing is built-in FPSLogger. There's also a class for that, which is called FPSLogger. I think that one also cannot be created before the creates lifecycle method, so we will also create that here below. And there, what you can do, you can simply say FPSLogger log. What that does, if I remember correctly, I think every second or every 5 seconds logs the current frames per second to the console. 1 second. Okay, so every second it will print the frames per second to the console. And it uses here GDX app log. And that one also needs to be set maybe initially in our game class here. So GDX app log level. And there is application log level debug, which means all the GDX app debug messages are shown. If we go to error, then only the error messages are shown. If we go to info, then info and error is shown. And if we go to none, then nothing is shown from these debug messages. But in our game, since we are developing a new game, we want to have all the debug messages, info and error messages available. So we set the log level to debug. And now when we start our game, then every second, okay, we have 0 FPS at the beginning. Most likely that's the initialization process. And then you see 166, 165, because my screen has a heart rate of 166, if I remember correctly. And I think VSync, so vertical synchronization, is enabled per default. So that's why we always have here the maximum amount of possible frames for my specific setup. Good. And the last thing, because we haven't seen that yet, there we also see the diagnostics of our asset service. So we see that it loaded the graphic, the tileset PNG, which is of type texture. And there was one reference, because that is the reference of our tiled map. There is the player, house, and oak tree graphic loaded as well. Those are our objects in the tiled editor. And there's a tiled map itself, which depends on the different textures that we have here. And when we call AssetService dispose, or if we would dispose just the tiled map, then all of these references would disappear and the resources bound to that are getting freed. Okay, that's it. That was, for me personally, a completely different approach that I used in the other tutorial series. Please let me know what you think about that. It was a little bit of a longer part, but that really covers, in my opinion, all the generic things that every game requires. So we covered the Spritebatch, we covered the viewport with the camera, and that we use arbitrary world units instead of pixels. We implemented an AssetService implementation, which can be reused in different games. And we learned how to profile, in that case, for example, the graphics interaction with OpenGL, and also to get some basic frames per second information with built-in LibGDX classes. And finally, we have the screen cache, where, by the way, we forgot to add the remove screen method, but yeah, we will implement it when it comes to that. But yeah, that's it. So we have now something working in our game. We have the first screen, we render the tiled map, and in the next part, what we are going to do, we are refactoring our current approach, because currently in our game screen, we have the logic simply in that screen here. And you can imagine the bigger the game grows, then the uglier this class gets and the bigger it gets, and it will get hard to maintain. So in the next part, we will learn something about a specific architecture pattern in games that we will use here, and we will then refactor all of that into a different architecture. But that's it for this part. Thanks for watching and have a nice rest of the day. Bye bye.